Hello, this is Carl Freund again with Cambrian-AI Research. And today it's my distinct honor and privilege to have Aart de Geus, the co-founder, chairman, and co-CEO of Synopsys. So welcome to Cambrian-AI Visions, Aart.
Well, thanks for having me, Carl.
It's a real pleasure. I've been following you for the last half a year or so in earnest, because I find the subject you're talking about a completely rethinking of performance at a system level and how you design for system level optimization and the use of AI and the role of EDAs. If you don't mind, can we just start at a foundational level for those audience members who have not heard you talk about Sysmore? Let's just start there, okay? Tell us, what do you mean by Sysmore?
Well, it's a great word, right? Because it's a whole new era of design. And you already used some of the words, which is system in contrast to just chip. And let's not forget, in the 1990s, we coined the term system on a chip, right? So we've done complex stuff for quite a while. And as a matter of fact, really what's happening with Sysmore is that 3 or 4 things are all arriving at the same time that warrants the name. For starters, of course, the last 35 years, which is mostly of the digital expansion age of Moore's Law. And so many people say, oh, it's dead. No, it's not dead. It has slowed down somewhat, but it's still pushing. And actually, people are now talking about 20 angstrom, right, as a node. That's pretty cool. I noticed that the word angst is an angstrom. But nonetheless, it's continuing. Secondly, of course, you have suddenly this conjunction of big data and machine learning. And they're arriving essentially at the same time. After cracking the Go game, suddenly the door was open. We've got to be able to do something with that. So that's arriving at the same time. And then, of course, people say, well, that machine learning thing, that's pretty powerful. If I just had more computation. What do you mean, even more? Moore's Law? Well, yeah, it's only that. But what about give me 1,000x more? Now, that's a big number. And of course, the first thing you say, well, the way to get there is why not change architectures so that they are specifically well suited for machine learning, not any different than architectures that were suited for graphics design, graphics chips. Now, of course, chips being designed for machine learning. And so you put all of these things together and suddenly you arrive at an ambition for the world that says, hey, machine learning, that's really the opportunity for every vertical market to become smart in some way or another. And I don't have to tell you, the impact would be huge for that. And so you put all of these things together, you see essentially that we've moved from Moore's Law as scale complexity to now the equivalent in system complexity. And so Sysmore stands exactly for that. The Sys part is, of course, systemic complexity. The More part stands for the ambition, the exponential ambition that we'll never give up on. And by the way, that we need, because 1,000x, that's adding quite a bit in terms of productivity.
Exactly. I mean, if you look at the largest models today, they were still smaller than 1,000-fold smaller than the cerebral cortex of the human brain. And we've seen a lot of announcements lately about extremely large models, not just GPT-3, but recent announcements both from China and Silicon Valley. Back to the designers of these.
But before you go there, you just said something interesting, which is then the human brain. The thing that we always underestimate, the human brain does this with 14 watts.
Yeah.
And, I look at my mom, 14 watts. Well, she had a lot of smarts for 14 watts, right? And therein lies this unbelievable quest that we're heading towards, because the advances have been fantastic. And I know you're going to go there. At the same time, that 14 watts, man, that horizon is going to be hard work.
We'll never get there with simulating neurons. We'll have to actually have, silicon neurons. But neuromorphic computing is still quite a ways off, I think, from a production capacity. But even the simulation of neural network activity and deep neural networks is just producing phenomenal results. Unfortunately, it takes a lot of money. It takes huge systems, supercomputers, and it takes a lot of power, which is impacting the environment. So if you're a designer and you're thinking about all this power supposedly available in AI, how does it make you a better designer? How does it help you get your chips to market that are better chips, more power efficient chips, higher performance chips?
Okay, well, there are two steps. And the first step actually is much more broadly already in use than people think, which is, of course, we have 35 years of super highly optimized algorithms in all of our tools that do optimizations, do simulation and evaluation and all that. And all of these algorithms are fundamentally, if then else algorithms with some heuristics in it. Well, the heuristics are essentially variables to tune your algorithm, right? Well, we do the best we can, but now we've applied machine learning to those very variables, and they have actually brought about some quite amazing advances in individual tools, and it often comes as a jump because we can look at more data that a human could easily do in more dimensions. Now, really the breakthrough that you're talking is the fact that now we've applied this not to individual tools or individual steps, but a succession of steps, which is essentially called a design flow. And, in a design flow, you have so many variables, not only in each one of the tools, but each of the steps, how you set your constraints, how you set your optimization criteria, how many times do you want to do this thing versus that thing. With other words, you're exploring a design space that is enormous, right? Many power to the 10x, 100,000 zeta, and so on in the exponent here. And so this is where bringing together the ability to look at that much data, making some inference as to where the best places in the space are, which, in olden times we called find a local minimum, right? Or find the global minimum, ideally. Now we're talking about a space that is much more multidimensional. And so that is extremely difficult for a human when the data increases, but also when the steps increase. And to take an analogy of 35 years ago, Synopsys started with synthesis, which was really one of the two automation steps, the other being place and route, that ultimately launched the rocket of Moore's Law digital from a design perspective. Well, there were other people that had invented great things in synthesis before Synopsys, but what Synopsys had, most people don't know, is we did synthesis and timing at the same time, and by the way, we could also optimize for silicon technology. And right there, that is already difficult for the human because you have to look at not only the gate count, but what is the critical path, and how do you find out if you change something here, it's going to not mess it up over there. And so that automation at that time was revolutionary. And, we forget that we were talking about, a few hundred to a few thousand gates. That's how small the problem is compared to today. But it was a step of automation that was not reachable by the human. Well, today we are looking at doing all of these steps, much more sophisticated synthesis, followed by the place and route, under timing constraints, under power constraints. Oh, and by the way, you have a test network that you can't mess up. And you then actually need to verify that it's physically, absolutely ERC, DRC correct, because otherwise it doesn't work. We do that all at the same time. And the AI system, the design space optimization system that sits on top of that, runs that and can start with the starting point a human would do and then explore from there. Or by now, we actually can also learn from scratch how to do that.
Amazing, just amazing. It's almost like playing the game of Go on using deep learning, but you're actually designing chips that play the game of Go or anything else.
Well, yeah, actually, we say sometimes AI for AI chips, right? To design AI chips.
People say is quite scary.
Yeah, but that's the same as the robot that's going to fix itself and then ultimately eliminate you, right? It works great in movies.
It's a Hollywood theme, and there are some executives who have chimed in to help add volume to that, but I think it's noise, certainly in our lifetimes. So what's the client's response then to DSO.ai? I mean, I know Samsung has publicly stated that they used it for the Exynos chip, but in general, has there been reluctance? Has there been eagerness to adopt? Or what's the rate? What's the pace of play here?
Exactly the same as when synthesis came in. Some people, immediate great enthusiasm, but does it really work, right? Others like, Well, I want to see the results of others before I invest in it. And, it's the same story as then in the last decades, which is run with whoever runs fastest. When you have a breakthrough, don't wait for people to be convinced. Run with the people that are willing to be convinced and take some risks together. And invariably, those are the winners in the field as well. And so since then, which is not that long ago, we have many processors, AI chips, graphics optimized chips, all going now through this. In some cases, it was enormously large blocks. And invariably, the results turn very positive within just a few months because it takes some time to set up the whole system. This is not like, just use one tool and no, you need to set up the system, the flow. You need to make sure the libraries are characterized correctly. And in many cases, actually, it has empowered the sort of the architectural level thinking just above because it provides automation below. And, automation can also be another word, right? It's estimation for the person that sits on top. Because if in a few days you can get a good result, you can say, if I change my architecture, am I in a completely different part of the search space? And that values architectural experience even more in the hands of the people that have the power to look down.
I think that's a great example because I firmly believe that AI will not replace us. It will help make us better at whatever we're doing. It gives us a level of tools that can understand data spaces that are beyond our capability. And as you point out, the dimensions. But what's the biggest impediment? What would slow things down?
Well, the impediment is always the same, actually, with all tools in the past, which is the most interested people are the ones that are most sophisticated, and they're also doing the most difficult designs in the first place. And so they have a very keen interest in knowing, am I taking a risk that screw up my schedule, or am I taking a risk that could make me meet my schedule or even beat it? And so their experimentation is always, how can I do some experimentation without jeopardizing the train that I'm on because that thing is already late? All schedules by definition start with the word late, right? By the time you have a good idea, you're already late on executing. And so that's not any different. But what has been quite amazing is that a number of the initial people that we've collaborated with, and you mentioned Samsung, which has been public about this, but there were half a dozen other companies that were just as well capable of doing advanced designs. They have now, meanwhile, had many good results and quite a number of not only tape outs, but now chips coming back. And so the Hot Chips conference was interesting because it was the first time that I communicated a broader perspective, not only of how important this Sysmore era is, that now allows for system on a chip to become system of chips, but also that this ability to translate this into smart by virtue of machine learning applied to a design flow was of interest to many of the end markets. And so the end market itself is actually saying, hey, this is interesting stuff. And so surprisingly enough, this presentation has not only been reported on broadly, but also been sent to other people. And I get messages from executives that normally would never, ever take the time to even look at a video of anything that say, hey, I looked at this. Does my team know about this? And sometimes they do, and sometimes they don't, and sometimes they do, but they decided to wait a little bit, at which point in time the exec says, hey, these numbers are really good. How come we're not using it? And so it engages in a dialogue, and that very quickly leads to experiments, and the experiments very quickly lead to some good results.
Yeah, I've had similar conversations with many of my clients who are typically designing AI silicon. And I asked them, are you using something DSO or internal tools to help you apply AI to optimize for your business objectives, for your design objectives, whether it's for power, performance, or space? And the result has been, we're interested, but we're not doing it yet. or they'll say we can't talk about it. And if they say we can't talk about it, that means they're probably doing it.
I can't talk about it mostly means I don't want to talk about it.
Exactly.
No, but as with the experiments originally, so as we started to get really good results in 2020, the initial results was to essentially do something that is as good as what the designer group could do, but in a rapidly decreasing amount of time. And then it became with also fewer people. And then suddenly we crossed the boundary of better quality of results. And you may know that I always look at everything we do in terms of three axes: the quality of results, which invariably is of course performance and power. Those are the drivers today. Then the time to results, which is really elapsed time, and how many people do you need to get there. And then the cost of results. And the big cost of results is ultimately, can you make the chip as small as high yield? Because area used to be the substitute for cost, but today it's really a combination of that and yield and so on. And then of course the design cost matters as well. And so what is on one hand surprising, on the other hand frankly is not, is once you cross the boundary of getting as good or better results than a human, after that, our job is optimize the heck out of that, right? And get it in a shorter amount of time. And by now, on all three dimensions, we do better.
So do your clients typically use cloud resources to do the training of the AI models, or are they?
In some cases, they do. The reality is, all these advanced guys, they have their cloud in-house, right? I mean, they have a lot of compute. And so even those people who have a lot of compute use external cloud sometimes when they have peak needs. And so yes, in some cases they do that. But it's turned out that our compute efficiency is actually relatively good. And so it's not like suddenly we're bringing, you see the lights going down in the building because, they're running a DSO run, right? No, it's not that.
So last question for you. Do you see other areas where AI and machine learning can help in the design process, specifically in verification? I was recently hosting a panel in DV Europe, DVCon Europe, where we had a lot of designers talking about how they're applying AI and ML to, and really more machine learning than deep learning, for improving design verification. Is that an opportunity area that you're pursuing as well?
Oh, absolutely. And I think there are many of those. Some of the characteristics that they have in common is A, if you have a lot of data, B, if you have heterogeneous data, so data from different things that somehow interacts, and where somehow is exactly the word, which is you sort of know what it does, but it's too much and too complex for a human to see where is the balancing. And balancing is just another word for optimization. And so you have optimizations just to make a simulation run faster, for example. You have optimizations of let's say, the test field. You have all these vectors that are supposed to cover a lot of potential errors. Well, the order of the vectors is actually very material how to get there. One of the deeper, very interesting areas is called DTCO, Design Technology Co-Optimization. And it builds on the fact that when you develop new technologies, silicon technologies, today we're rapidly moving from an era where everything is an experiment. Okay, I want to make the gate a little thicker or thinner, add some other chemical into it. You of course can do that with experimentation. It's very expensive, it takes a long time. But increasingly that is now becoming modeling of the interaction of materials, the interaction of layers, and of course the actual electrical behavior of the structure until you have a transistor and then a gate and so on. And so what that leads to is if you can computerize part of that, then you still have the question, well, if my transistor is better in this or that way, how much impact does that have? Because the transistor is a really small device in a really complicated system, right? And so this is where this notion of co-optimization between technology development and seeing the impact in the design is highly enhanced by having EDA, because we can say, well, why don't we take a processor core and you make these technology changes, and let's go through the whole flow and see how good this core comes out. Well, if you can do that, why don't you start doing multiple experiments in this loop? And why don't you apply machine learning to say, well, this is the variable that, if you tweaked it a bit more in this direction, would actually have the biggest impact on this complex circuit. And, in many ways, is that really different than design centering in 1970 using that new program called SPICE? Well, it was difficult then too, but people essentially did, Las Vegas style, let's just do experiments and see the sensitivity of the circuit. Well, now we're looking at a much broader design flow. And that is why I think we have a far and big horizon of optimizations that we can do. And some will be easier than others. But over time, much data, much different sources of data, and a multi-step process. That is what a design space is really all about.
Yeah, sort of reminiscent of the early days of using deep neural networks in supercomputing, where a few crazy scientists at Oak Ridge National Labs said, oh, let's just try this out. And people said, no, you can't do that. Now, of course, people realize that the most cost-effective way to get a simulation done 1,000 times faster is to not do the simulation at all, but to simply estimate what the simulation would produce if you actually ran it. And now all supercomputers have AI elements. It is a complement to traditional simulation science. I think the same thing's going to happen in EDA. I think we're in the very early days of machine learning optimization.
Yeah, and you used a very important word, which is this word of estimation, because estimation has always been the way you made decisions at a higher level about stuff that wasn't built yet, right? And actually, estimations through the word simulation have become actually very, very good, except for one category, which is that there are certain things to estimate what happens in the circuit is difficult because the activity level is determined actually in the software. And dynamic power, of course, fits that to a T. And here too, I think the breakthroughs are quite amazing, because we now have systems, hardware systems actually, to create a prototype of the design that you don't have yet, right? That's not implemented. So the prototype is a model, and we can run software on it, use that to diagnose the level of activities at multiple levels, all the way down to the number of transistors switching. And we use that information to apply machine learning to optimize, again, in this design space exploration to optimization for the dynamic power of that specific software. Now you say, well, if I have 25 different software pieces, now how many of those do I need to all optimize for? But the fact is, a lot of this stuff is actually going towards specifically machine learning algorithms again. And so you truly get the software-defined hardware, right?
Absolutely. Fascinating. I could talk to you for hours about this, or listen to you for hours about this. You've got some wonderful perspectives and vision for the future.
Well, it's great to talk to you. You know a lot, so that's cool.
Well, thank you. I really appreciate you taking the time to join us today. Look forward to talking with you again soon. Hope you stay well and be well.
We'll do some breakthroughs until next time. So,
Take care.
thank you, Carl. Be well.